Thanks for watching my video today. Let's see again the partial fraction expansion of cosecant x. Okay, then is cosec x is equal to 1 upon x plus 2 times sum from unequal to 1 to infinity minus 1 to then x upon x square minus pi square and square. For x upon pi is not belongs to the integer. Okay, now we are going to use integral representation of gamma s, gamma 1 minus s. Okay, we know that, so integral from 0 to infinity x to the s minus 1 upon 1 plus x dx. This is nothing but pi over sine pi s, right, which is nothing but gamma s, gamma 1 minus s. This we have done in the earlier. Now let me equal this integral to bi. Now we are going to use to prove this partial fraction expansion of cosecant x in using integration. Okay, so we know that this integral is equal to this. So okay, now we are going to deal with this integral now. So integral I is equal to integral from 0 to infinity. I can split up into 0 to 1 to 1 to infinity. Okay, because using the property of indefinite integral from a to b, f dx is nothing but a to c to b, right? So like that, integral from 0 to infinity I can split this 0 to 1 x to the s minus 1 upon 1 plus x dx plus 1 to infinity x to the s minus 1 upon 1 plus x dx. Okay, now we are going to keep this s in this and we are going to do substitution method here. Now put x equal to 1 over x. Don't confuse this to x. This x is nothing but this x. Okay, and this x is our new variables. Okay, so dx is negative 1 over x squared dx in second integral, this one. Okay, I is equal to integral from 0 to 1 x to the s minus 1 upon 1 plus x dx. This is nothing but this plus, now the chance is this one. Now if you put this here, x is equal to 1, so it will be this x will be 1, right? If you put here infinity, so this x will be 0. Okay, so I hope you understand the upper and lower limit of this integral. Now this x is nothing but 1 over x, so 1 over x s minus 1 upon 1 plus x is nothing but 1 over x into this dx is nothing but negative 1 over x squared dx. Okay, now I is equal to integral from 0 to 1 x to the s minus 1 upon 1 plus x dx plus, now because of this negative, why is this? Because we know the integral from a to b f of x dx is nothing but negative times b to a f of x dx. Okay, then is property of definite integral. Okay, because of this minus you can interchange this upper and lower limit. Okay, therefore because of this negative, so I am going to interchange the lower and upper limit 0 to 1, and this will be x to the, if it come out here, then it will be 1 minus s. Okay, and this actually it will be 1 over x to the s minus 1 is nothing but x to the negative 1. Okay, s minus 1, so it will be x to the negative, so negative s, negative plus 1. Okay, therefore 1 minus s, so it is 1 minus s upon, so 1 plus x upon x into 1 over x squared dx. So I is equal to integral from 0 to 1 x to the s minus 1 upon 1 plus x dx plus integral from 0 to 1, so here this and 1s will be cancelled here. Okay, and here 1s will be taking here, so it will be negative, right? X to the 1 minus s, this one, because of this negative x, so it will be negative 1. Okay, upon 1 plus x dx. Now I is equal to integral from 0 to 1 x to the s minus 1 upon 1 plus x dx. This is the same thing. Okay, plus integral from 0 to 1, so simplify this, x to the negative s upon 1 plus x dx. Okay, now we have come to this. Now we are going to use, now we know that 1 over 1 minus x is sum from unequal to 0 to infinity x to the, and this is nothing but geometric progression. Okay, gp. So if you put, and therefore this one 1 over 1 plus x is 1 over 1 minus negative x, right? So negative positive, because I'm trying to prove in terms of this one. So sum from unequal to 0 to infinity Here x is nothing but negative x, so it will be negative x to the n, right? Negative x to the n. This is nothing but sum from n equal to 0 to infinity, negative 1 to the n into x to the n. Okay, so in place of this, I mean this denominator of 1 plus x, we are going to substitute the summation. Okay, that's our goal. So I is equal to, so 1 over 1 plus x is nothing but this one. Therefore sum from n equal to 0 to infinity minus 1 to the n. So this sum and integral interchanging. Okay, so integral from 0 to 1 x to the s minus 1 into x to the n, right? X to the n dx plus sum from n equal to 0 to infinity minus 1 to the n integral from 0 to 1 x to the negative s and x to the n dx. Okay, now I is nothing but sum from n equal to 0 to infinity minus 1 to the n integral from 0 to 1 x to the, combine them, n plus s minus 1 dx plus sum from n equal to 0 to infinity minus 1 to the n integral from 0 to 1 x to the n minus s dx. Okay, now continue it here. Continuation will be here. Okay, now I is nothing but sum from n equal to 0 to infinity minus 1 to the n. So integration of this will be x to the n plus s upon n plus s, right? From 0 to 1 plus sum from n equal to 0 to infinity minus 1 to the n. Integration of this will be x to the n minus s plus 1 upon n minus s plus 1 from 0 to 1. Okay, so therefore I is equal to sum from n equal to 0 to infinity minus 1 to the n upon n plus s. When n is equal to 1, so 1 to the any power is just 1 and 0 is just 0. Okay, you get minus 1 to the n upon n plus s. So if you put here the value 1 and 0, you get sum from n equal to 0 to infinity minus 1 to the n upon n minus s plus 1. Okay, now which is equal to, so sum from n equal to 0 to infinity minus 1 to the n plus s plus, and this is just the same thing as if you start from 0, that means it will be minus s plus 1, right? And if it is 1, so 2 minus s, right? And so in place of this, so in place of n plus 1, I'm going to start from n equal to 1 to infinity minus 1 to the n minus 1 to the n minus n upon n minus s. This and this summation are same thing. Okay, so you get, so in this I'm going to start from 1 again, this also. Okay, so at 0, at n equal to 0, you get this is minus 1 to the 0 is just 1, right? This is 0, so it will be left with 1 over s. So 1 over s plus sum from n equal to 1 to infinity minus 1 to the n upon n plus s. So this is, there's 2 negative here, right? So negative 1 to the n minus 1 is same as negative 1 to the n into negative 1. Okay, into negative 1. So this negative and this positive will be become negative. Sum from n equal to 1 to infinity minus 1 to the n upon n minus s. Why I did so? Because I want to combine these two. Okay, which is equal to 1 over s plus, now let's combine them. Sum from n equal to 1 to infinity minus 1 to the n, same thing, right? 1 over n plus s, this one, minus 1 over n minus s. Now this one, now combine them again. I is equal to 1 over s plus sum from n equal to 1 to infinity minus 1 to the n. So if you combine them, you will get n minus s minus n minus s again here, right? Upon n plus s n minus s, which is equal to 1 over s plus sum from n equal to 1 to infinity minus 1 to the n. So what can we cancel? And then we can get cancelled, so it will be negative 2s, right? This one 2s, and this is n plus s, n minus s is nothing but n square minus s square, right? And you get I is equal to 1 over s minus this minus coming here 2s sum from n equal to infinity minus 1 to the n upon n square minus s square, which is 1 over s. So this one interchange it then with this one, this negative, then you get positive of 2s sum from n equal to 1 to infinity minus 1 to the n upon, here is start from 1, right? So if you interchange this, because of this negative, so it will be, this will be positive and this will be negative, meaning s square minus n square. Therefore 1 is our original, So let's see our I. One is our I here. Our I is nothing but this, or integral this, and this integral is nothing but this one, right? Pi over sine pi s. Therefore, pi over sine pi s is equal to this summation. What is 1 over s plus 2s, sum from n equal to 1 to infinity minus 1 to the n upon s square minus n square. So this is another one, okay? Now this is the partial fraction expansion for pi over sine pi s, okay? So in order to get cosec, okay, always note that 1 over sine x is nothing but cosec x, okay? Okay, this is trigonometric ratio. So in order to get this or cosec, so I'm going to substitute. So I'm trying to eliminate this pi, okay? Just take out this pi. So in order to take it out, so I'm going to substitute s equal to x over pi, right? We get pi over sine pi into s is nothing but x over pi, so that these two can get cancelled, okay? Which is equal to 1 over x over pi plus 2 into x over pi, sum from n equal to infinity minus 1 to the n upon s is nothing but x over pi square minus n square, so which is pi over sine x, right? Pi over sine x, which is pi over x plus, here if you take the reciprocal, then you'll get x square minus this pi square coming here, pi square n square, and this pi square will be coming out here again. So this is this one, okay? Pi square, and this pi and this 1 pi will cancel out. Then you get pi over sine x is nothing but pi over x plus 2x pi, sum from n equal to 1 to infinity minus 1 to the n upon x square minus n square pi square. So this pi, this pi, this pi cancel out, okay? So you get 1 over sine x is 1 over x plus 2 times sum from n equal to 1 to infinity minus 1 to the n. This x bring out here x upon x square minus n square pi square. Therefore, we know that 1 over sine x is cosec x, right? Therefore, cosec x is 1 over x plus 2 times sum from n equal to 1 to infinity minus 1 to the n x upon x square minus pi square n square. Right, this is all. Right, this is exactly our proof now. Again, pi over cosec pi x, meaning this one, okay? Pi over 1 over sine is nothing but cosec. Pi over cosec pi s is nothing but 1 over x plus 2 times sum from n equal to 1 to infinity minus 1 to the n x upon x square minus n square. Okay, this and this is the same, okay? So this is how I managed to prove the partial fraction expansion for this cosec x, okay?